Yeah, sure. So there's been a lot of stimulating confusion and disagreement here. Of course, as physicists, we find nothing more stimulating than confusion about not being able to understand something properly. I hope, well, I know I at least will not be immune from the disagreement part. And in fact, I contemplated a much simpler title, none of the above. But I decided to be a little more descriptive and talk about what I think we should be doing, rescuing quantum mechanics and approximate space-time, and talk about an approach I've been pursuing to try to do that. This is a kind of long string of references. AMPS appeared somewhere in the middle here. And there is various work in progress and in preparation as well, so things still coming out. So for the purposes of addressing this problem, there are some things I'm going to at least choose to believe in. One is quantum mechanics, because it's very robust, quantum mechanics is, and hard to sensibly modify without getting into really crazy situations like massive violations of energy conservation. The second is space-time, at least approximate space-time. So I have in mind that space-time may not be a fundamental, probably isn't a fundamental construct, and ultimately likely arises from some deeper quantum structure. But, you know, that's what we really observe. We can probe space-time, so it's a very good approximate concept. And moreover, I think it seems to me it should be a good approximate concept, at least with certain limitations, which various of us have explored, for the examples also of big black holes and cosmologies, which are in some respects very similar. And then finally, local quantum field theory as an approximate description of the dynamics. Of course, that's the best description we have to describe all of the various experiments that we've carried out so far. And so the big question is, can these things be reconciled with black hole evolution? And this is where all the confusion starts rising. So let me start with a proposed picture, and then I'll try to fill out some more of the details. So I'll start with a known picture, just the classical picture of a black hole in Eddington-Finkelstein, in an Eddington-Finkelstein picture with the horizon and singularity. And as John reminded us, you know, stuff goes into the singularity, and of course that's one of the things we worry about. What we really mean by stuff is, of course, quantum information. That's a more precise notion of stuff in quantum mechanics. So a picture of stuff going in, well, one way of getting quantum information into the center of the black hole is just naturally through letting a black hole evaporate. And the Hawking process, as we know, builds up this entanglement between degrees of freedom that go in and degrees of freedom that come out. Or we could just as well, say, take EPR pairs that we had prepared and throw in one member of the pair into a black hole, and that would be a very similar picture. So actually, I'll just stick with this picture. So this is the now semi-classical picture of what black holes do. And of course, it's not the complete picture. So how does it need to get modified to be consistent ultimately with quantum mechanics? Well, I don't think anyone would object by my saying that we expect the singularity somehow gets smoothed out into some more regular region that is not truly singular, although we don't understand its dynamics, but I think we... Like I said, well, I won't be immune from disagreements, but...
I wouldn't have that except that you said no anyway.
Oh, you just did it to be contrary. Well, so, okay. at least this is quite plausible. Well, people who don't like to think about the inside may also object, but let me add that caveat too.
So what happens now to your Penrose diagram when you smooth out?
We could just as well rescale this and put this in a Penrose representation, but the reason I will not draw a Penrose diagram in this talk is because I think Penrose diagrams obscure certain things, and it's for many purposes. Thank you, Tom. For many purposes, it is more helpful to draw things in pictures like this, the Eddington-Finkelstein-like pictures.
Well, I guess my question is, to what extent do you, once you sort of smooth out the singularity, how are you going to define your black hole once you're going to have to change the causal structure, right?
Well, there's something called, say, an effective horizon, which is the last light ray that gets out before you hit, say, well, the edge of this stuff is when, very high curvature, very high concentration of whatever the description is in the center of the black hole. So I would draw a Penrose diagram like that, bearing in mind, of course, this is not an exact picture either, because I don't have in mind that space-time is an exact picture. Okay, so what else do we need? This is not enough. Stuff goes in and stays in the middle. By quantum mechanics, if stuff goes in, stuff has to come out. So black holes should leak information somehow, and here's just, again, a picture for how that might happen. That information ultimately leaks out of this dense region at the center and into degrees of freedom near the horizon, and then those can escape off to asymptotic infinity. Now, of course, a problem with that is that kind of leakage involves some kind of non-locality or superluminality, at least with respect to the semi-classical geometry. And of course, this goes all the way back to even this old massive remnant scenario where it's a more violent kind of superluminality. And this is also, I think, it seems to me, people have largely agreed part of the story of how fuzzballs would have to work. Although, well, in the fuzzball case, there's dissent whether the black hole even forms. And so that would be a different kind of, at least some assert, non-locality. I think that's essentially the right story, that you require something like this going on. Also, with the firewall story, initially, presumably, you make a black hole, and at some point it transitions into something outside the horizon, and so you have superluminal transfer of information. But I'm interested in seeing whether we can find a more innocuous form of information transfer that's more nonviolent and doesn't destroy the horizon, so it saves approximate space-time and approximately saves the equivalence principle and so on. And I guess one of the guides I'm going to take in this actually is something Lenny said, but I'm going to push it a little bit further. He said in his Blackboard talk that black holes are like sort of ordinary things. You added the caveat from the point of view of the outside, but I'd like to think of them as ordinary things even with respect to the inside dynamics as well. Okay, so how could we describe more carefully such a picture? First of all, from the fundamental point of view, it seems to me that we might have a picture based on, say, quantum subsystems so building up a Hilbert space from tensor factors. And here is a picture of such subsystems that might, that match the picture I drew on the previous slide. You have a Hilbert space of the states at the center of the black hole where we really have a manifest breakdown of the field theory approximation. Then there's a region inside the black hole. If you've just fallen in, you can still do experiments described, at least most of us believe, by local quantum field theory. And so there's a region that is at least approximately described by usual space-time physics before you hit the singularity. Then the region outside the horizon at r equals r, but nearby, and then an asymptotic region that's, say, larger than 5 or 10 times the radius of the black hole. So we have these nested, these different subsystems, and all of the states should be contained in a product Hilbert space. And local quantum field theory, well, we also want unitary evolution on these subsystems, or on this big Hilbert space. And unitary evolution rearranges the excitations or the degrees of freedom. Also, in one way of thinking about it, in the Hawking process, creates degrees of freedom. That's depending on how you describe it. So the ordinary evolution of local quantum field theory involves, say, exchange of degrees of freedom between the near and far regions, just outside the horizon and infinity, but only transfer of degrees of freedom from, or more precisely, transfer of information from near the black hole into the black hole and not the other way. That's what black holes do if you treat them, well, by quantum field theory on a black hole background. And likewise, local quantum field theory only transfers information more deeply into the black hole as you evolve forward. But that's the problem. It's not unitary if you only have these processes. So there have to be some extra contributions to the unitary evolution that transfer information, quantum information, from, say, the core states of the black hole to at least the immediate vicinity of the black hole. And I'm not going to try to go out further than that. Let's just think of, because I don't want non-locality spanning the universe, let's just think about transfer to the immediate vicinity of the black hole. So you might try to build up a fundamental description along these lines. I'll have a few more words about that later, but that's not what I'm going to do here. What I'm going to do is try to describe this in an approximate way as a deviation from local quantum field theory. So this is not yet a complete picture. In fact, I don't think it's likely a fundamentally correct picture. Again, if space-time is not the right, and local quantum field theory is not the right sort of way of thinking about things, it might be a little bit like in the example of the atom, and this is one I keep coming back to, the transition from classical physics to quantum mechanics and what we learned in trying to describe the atom. It might be in that context a little bit like trying to parameterize quantum effects in the classical atomic picture. So that's sort of not really right, ultimately. We could try to do it, and in fact, that's roughly how Bohr started, is with the classical picture and then trying to parameterize what happened. So I'm going to try to parameterize things in a way that I think is presumably not quite the fundamental correct picture, but we might get at some element of the truth nonetheless. And so how do we do that? Well, according to what I've said, we need something that transfers information from inside the black hole, near r equals 0 in the conventional picture, to just outside. And in some time slicing, we could write down a Hamiltonian that does that, which involves operators that basically annihilate excitations here and create ones here, or vice versa, with some sort of propagation kernel. Just to touch bases with something people, at least some people in the audience know, if we put in constant values for these inverse propagators, we'd be back to the story of wormholes, space-time wormholes, where we don't transfer information, but with a background-dependent and space-time-dependent function there, clearly this kind of interaction can transfer information. And what kinds of operators might we put here? Well, say just the field operators or the stress tensor or various other things. Of course, that's a poor representation of what's going on here. So really, again, this is not yet a complete picture. But I'm trying to parameterize how information transfers out. Now, in fact, I'm not going to focus so much on the inside because a main question of this workshop is, can information get out without destroying the horizon? It's been a major theme here. And for the purposes of addressing that, we really just need to focus on the region around the horizon. And so to do that, I'll make what I'll call the effective source approximation. We take all of this stuff that describes the internal dynamics of the black hole and just lump it together in a source and call it J. So that's a little bit like thinking about, say, a radio antenna that emits, electromagnetic waves. And of course, the radio station and everything going on at the radio station is described as, well, fundamentally a quantum system. But for many purposes, I can replace all of that just by an effective source that's producing the outgoing excitations. And so I'm doing very much the same kind of thing here. So these sources, in principle, are correlated with the internal states of the black hole, but let's just describe them for now as classical sources. And so again, in the kinds of examples that we might try to exhibit, we could think about a coupling to the fields. Of course, you have to be careful to write down things that are gauge invariant and so on. These are toy models. Or say a coupling to the stress tensor or to the other operators in the vicinity of the horizon. And so a question getting at this main theme, can information get out without destroying the horizon, is, well, for the purposes of near-horizon dynamics, can such effective sources, first of all, convey a strong enough signal to get the information out, and what size do they need to be to do that? But at the same time, can they not have really violent consequences in the immediate vicinity of the horizon? So let's investigate that in a toy model. And I described the basics of this toy model 6 months ago, and then with a student here who actually I think will be on the market this year, we're filling in more of the details in a paper that should appear soon. So, yeah, Veronica.
So classically, I guess the horizon can ripple classically in all sorts of ways, but that's presumably not what we want to extract information from. I mean, that's nowhere near.
Yeah, so let's go back to this slide. And you may notice I snuck in here in small print, like horizon fluctuations. We don't have any picture of how horizon fluctuations do this, sort of store the information and transfer it.
But fluctuations means quantum ones or just classically rippling? I mean, the classical...
Either in a picture where we're talking classically, or in a picture where we're starting with the classical background and quantizing small perturbations about it. We don't have a picture of how horizon fluctuations do what I said. Okay? So we don't have a picture where this happens. Now, you might think what I'm describing, may ultimately be related to something like that, where you have some manifestation of the quantum information inside the black hole in something like horizon fluctuations. But again, we don't, I think, have any clear picture in our current description of how that works. But it's a little bit like that. Yeah?
Would you get the same sources outside of other compact objects like neutron stars?
I think probably not. I don't need the microphone. Anyway, I think not. And so these would be related to the fact that you're dealing with a black hole. And black holes are different than other objects in various respects. They have a huge number of, for example, ultimately internal states, far more than in a neutron star. And so at least that's one possible way of explaining why the effects are important for them and not for others.
But a black hole is a global quantity, right, having to do with the boundary of the past, the future, null infinity. So how are you going to preserve locality, right, and build up these sources?
I didn't say I was preserving locality.
Well, that's right, nonviolent, non-local.
So, I mean, ultimately one has to embed this in some more. Look, ultimately this has to be embedded in some, more fundamental, consistent picture, which we don't have yet. I'm just trying to parameterize, a scenario for how this could work. But I am allowing that that we need to do something to modify locality with respect to the usual classical or semi-classical picture. I think many people in their scenarios have agreed to that, whether they will say those words or not. In order to save quantum mechanics, that seems to be the game we're playing.
But it would be great if the modification was tested in other situations beyond.
Yes, say cosmology. But anyway, one step at a time. One step at a time. And right now I'm just trying to figure out how to explain why the immediate vicinity of of the black hole is not badly singular, for example, or confronting some of these questions that have been raised. Okay, other questions? Okay, so a toy model, let's just think about a black hole, free scalar field propagating on it, and let's consider the kind of source that I've described. Just say linearly coupled for now in this toy model to the scalar field. Yeah. Again, in this effective source approximation, I'm going to think of it as being classical. So particles. Yeah. Yeah. So ultimately. Yeah. Okay. So let's go back. Okay. Let me go back to what I said. Okay. So I have in mind that there are interactions between here and here. And so in that full picture, then you will have correlations between what's going on out here and the internal state of the black hole, if there are such interactions. But I'm saying right now, we just want to think about what's going on outside the horizon, because I want to address the assertion that in order to get the information out, you need something singular at the horizon, for example. Yeah. Yeah. Good. Well, yeah. Well, okay. So I'm going to describe in more detail what it does, but it creates outgoing flux of energy, for example. Sure. It's space-time dependent. It's like a radio antenna. If I turn on yes. Yeah. For the purposes of addressing the question of does this create singular stuff near the horizon, let's just make it classical. But I have in mind that through this picture, it's really something that depends on the internal state of the black hole. Okay, so I'm approximating this interaction as a classical source, again, just to address how it affects the immediate vicinity of the black hole. Okay, so, yeah.
If you have this extra flux of energy in addition to the Hawking radiation, how do you make sure that you get the correct thermodynamics, or supposedly you're modifying it by an order 1 effect?
Sounds like you saw my paper that came out last week, and I'll get there. So, well, probably, I'm sure other people independently realized there were issues there. Okay, so this is the model. We have some, for the purposes of thinking of things outside, let's think of this as a classical source. Again, it should be ultimately correlated with the internal state of the black hole. Let's parameterize it this way. So oscillation in, say, Schwarzschild time, decompose it, say, in the spherically symmetric case in partial waves, and then some radial wave functions, or some radial dependence. And what else are we going to put into sort of our assumptions about the form of that source? Well, there's a characteristic scale. There's one scale in the problem, at least naively, and that's the Hawking radius. So let's imagine that this source dominantly acts with the frequency, which is the inverse of that radius. You could generalize. You could have some power law dependence and still, I think, avoid the kinds of problems that one worries about. But let's just focus on this simple case. And for the radial dependence, let's suppose that the radial profile of the source is smooth at the horizon, so not wildly oscillating. And let's suppose it vanishes when you get far from the black hole. That's really all I think I need, although you have to ask, well, how big are these things? How big is the source? And there's a required size. If you want to be able to send the information out that has to come out, there's a required size. One way of putting it is once you're on the down part of the page curve, I'll show the page curve in a minute, you have to be going down at a certain rate in order to end up with no entanglement entropy, no von Neumann entropy at the end. So you have to go down at least as fast as basically corresponds to the Hawking rate. So the von Neumann entropy has to be decreasing at least by a scale or by a size set by that scale. And correspondingly, you need an energy flux if this is the characteristic energy of each excitation, which is comparable to the Hawking rate. And so that tells you how big these sources should be if you're going to describe, again, the kind of signal that can transmit the required information, again, bearing in mind that it would have to be a fundamental quantum thing correlated with the internal degrees of freedom of the black hole to do so. And so these are the characteristic scales. Again, the way I've parameterized it, everything just only depends essentially on R. Let's moreover assume that these sources or these interactions are present not just for the S wave, but for modes with higher angular momentum. And so that I'm going to take as my starting point. That's how I describe something that's sending out a strong enough radio signal to relay the information. Questions on that so far?
Maybe you'll come to this later, but I'm just worried that this is still too large. This might still give you very large non-local effects between the inside and the outside. I mean, if this J is really coupling to something that's near the singularity, this 1 by R cube is probably larger than what you want.
Well, it would be nice to hear, this is the effect it has on the outside, and we know that when you're going down the page curve, on the part where it's going down to 0, you have to have basically 1 bit come out per light crossing time. So that's another way of saying what I just said. And so that tells you how big the effect has to be on the outside. And then the question is, how do you get it from the stuff inside? And so there are couplings, and then there are also, the question of how many internal states do you couple to? And there are a lot of internal states you couple to. Then, once you take into account, that's where this size comes from, then one could ask the question, does that get you into some kind of objectionable situation? I haven't seen one, but maybe you'll think of one.
This is actually exactly the size of the commutator we estimated for some other reasons, but I'm just worried that would this lead to a non-local commutator between operators inside and outside that scale with this power, 1 by R cubed?
No, I don't think necessarily. No.
So these bounds you're basically getting in part from black hole thermodynamics, right?
No, I'm getting, and I'll come back to black hole thermodynamics.
But you're later going to modify it, right?
What?
You're later going to modify, what you call the entropy.
Yep.
And so then, it seems a little circular.
Well, let's come back to that. Okay? How fast does it have to go down? I'm just saying it has to at least go down this fast. If it doesn't go down faster, or at least that fast, then we're in trouble. If it goes down slower, you're sunk. Then you end up with too many degrees of freedom inside the black hole, too much von Neumann entropy, or too much entanglement entropy. You end up with a remnant, and you're sunk. We'll come back to that too, and I wouldn't say necessarily competing with, but we'll come back to that.
If it's competing, then it's only a little non-unitary, right?
If it's competing, it's only
if two things are happening and one of them violates unitarity and the other one doesn't, then I don't really care if the one that doesn't violate unitarity is happening faster.
Well, basically, at least a simple-minded picture, and this goes back to, in fact, these early models I wrote down. A simple-minded picture is that the Hawking process is taking place and building up entanglement, and this process is simultaneously taking place and decreasing the entanglement. And in the end, all the entanglement's gone. So I guess that's what you mean by competing, and this one wins. Okay, so let's go on to possible concerns about this, and in particular this question about whether you have bad things happen at the horizon. Do you have a singular horizon? Well, basically, with the fairly simple assumptions I've made, with a smooth J that's not super high frequency, you don't excite Planckian wavelength things down near the horizon as seen by the infalling observer. And in fact, you can check if you take the state, using coherent state-like techniques and the curved background, if you take the state that you get from this source of the kind I've described and look at the energy momentum tensor, say, for outgoing excitations, that's what I mean by T minus minus, in the Kruskal coordinates, which are the correct coordinates for infalling people, you find that you get something that is not singular. So that's in contrast to, say, the firewall story where this would be singular, or at least huge. So another way of stating it is this kind of source doesn't really produce, well, I already said this, sort of Planckian wavelength things down near the horizon. The state it does produce satisfies something like a no firewall condition that, again, if you think about things, say, in the Kruskal parameterization for the modes, you don't have, say, Planckian or cutoff size excitations excited by this kind of source. So in that sense, it provides a way of doing what we'd like to do, describe information transfer out of a black hole, without producing bad singularities at the horizon. Okay? Yep.
This is related to Daniel's question.
Yeah.
Are you assuming that the information content of the black hole is smaller than e raised to power s Bekenstein? Because otherwise, if what Daniel was saying is that if you have the Hawking process, it is non-unitary, and you can't. I mean, if
yeah, I will come back to that.
Okay.
Okay. It's been asked 3 times now in different versions. I will come back to that soon, in fact. Okay. So this problem of having singular behavior at the horizon, which, by the way, of course, was expressed well before amps. They just emphasized it strongly in a way that people like. That is addressed, at least in this limited fashion, by this kind of model. There are other things you might worry about. One is, what if I think about a really big black hole and I have this extra process going on? Do I have something that doesn't behave properly? And in particular, for a really big black hole, the Hawking radiation turns off. And so I go over to the Rindler space limit ultimately. Does this kind of process also turn off? And that basically follows from what I've said. The way the sources scale as you crank R up. In fact, I said that basically the minimal size for the excitations they're producing is to basically match of order the Hawking rate. So that goes away as R goes to infinity. So that's one sort of thing you'd like to have happen, and which naturally comes out. Another issue is that of mining. Another possible concern is that, well, for example, you could start with a black hole that had reached the page time, so it's maximally sort of entangled, and then you introduce a cosmic string into the black hole, and that means, or several, and that means the energy can get out more rapidly than Hawking would have said. And so the concern is if the information doesn't also come out more quickly, then you end up with something that I call an overfull black hole, where the von Neumann entropy is larger than the Bekenstein-Hawking entropy. And that's the kind of situation which is getting into the remnant scenario, which is bad. So how do we avoid that kind of problem? And by the way, let me just parenthetically say, coming back to this, I could give more details of how this works. I've got various slides on that, but I'm not going to do that, at least right now, and I can do it later if people want it. Okay, so how do we address mining? Well, so I said that let's suppose these sources are present up to some, well, for the higher angular momentum modes, first consider the case where there's no mining taking place. And then It doesn't matter if these sources are turned on, for the same reason that we don't really care much about higher L modes in the Hawking radiation. They don't get out. The escape of the higher L modes is suppressed by these tunneling factors, which get quite small as L gets large. And so Hawking radiation at higher L doesn't get out, and just as the same mechanism suppresses the escape of modes that would be produced by these extra interactions I've assumed. The extra interactions I've assumed do produce some extra stress tensor near the horizon. You can estimate the size of the stress tensor. It's of order Lmax squared over r to the fourth. And, well, you might worry, okay, if you take Lmax to infinity, that's a really big stress tensor. How big does Lmax have to be? Well, let's suppose it has to be at least big enough to match the maximum mining rate. And if you match the maximum mining rate, that gives you Lmax squared equals r. So this estimate gives you 1 over r to the fourth. So let's think about that. In the case of a solar mass black hole, you've got 1 extra unit of Planck energy per kilometer cubed from this effect. So it's small for big black holes still. Okay, so that's without mining. Douglas.
Maybe you're going to address this in a minute, but you might think that you could target the mode that you're going to mine so that you would need one of these sources coupled to every mode in the zone, not just like the 10 extra modes that Adam Brown allows, but that you would need a J source for every mode that in principle could be mined.
Yeah, you need something like that, and so going up to an Lmax, and Lmax could be even larger, is an attempt to target that. I'm not going to say a lot more about that. And there is the question about exactly what you can and can't target with mining. We need a more sharp description of mining, I think. So what I have in mind in this case, mining. What happens when you turn on mining? So the idea is that, let's suppose it's a cosmic string, and that these sources couple to everything. And for example, I said, let's consider the case where the source couples to the stress tensor, and then it will couple to everything. So they couple to cosmic string matter just as well as ordinary matter. So you lower your cosmic string into the atmosphere of the black hole, and the sources also interact with the cosmic string and the modes on the cosmic string. And basically what the cosmic string does is it opens up an extra channel for energy flow out of the black hole. There are extra modes for which there's no barrier now. And we know that increases the Hawking rate. Extra Hawking excitations flow out along the string. But also, if you have this kind of coupling, of course you expect that there would be extra excitations flowing out along the string that are created due to these interactions. And with the right rate, with the very simple assumptions that I've made. So in other words, the rate of information transfer, if we think of these J's as producing information transfer, increases commensurate with the rate of energy loss of the black hole. Okay, so one point I want to make is that these extra information carrying excitations are really, in a sense, present only when you are mining. And that, I think, is an important point. And there's a natural way of avoiding at least one part of what has been called a conspiracy. You need this extra process to turn on when you start to mine, and this is just a natural way to do it. I'd also like to, sort of quickly remind you of a story which some of you may know, the story of the word bag. Feynman has, in this interview, a place where in an old interview, he's talking about his son who announced one day that he couldn't say the word cat because his word bag had run out of the word cat. And of course, that, as we know, that's not how it works. His son, like many young kids, have rather interesting pictures of things. And so that's not how it works for words. The word is made as it comes out. But also, this is how it works for photons in the atom. The atom makes a transition. The photon comes out. There's not a photon bag where there are photons to begin with. It just is produced as part of the interaction. That's what Feynman was trying to explain. And I think in the same sense, there is not a mineable mode bag. And that comment is related to what I just said and may address some of the issues that have been raised in describing mineable modes.
Sorry, Steve, before you go on, I wonder, could you explain back up on the top where your estimate for the Kruskal stress energy that L max squared over R4 comes from? I'm surprised that, since everything is set by the Hawking scale, I'm surprised that you don't get something that looks like the naive energy of the thermal atmosphere of a black hole. It should be something much higher than that.
Well, let me give a quick answer, and then one can supply more details. But everything is set by the Hawking scale, and so this has dimension 4, and that's 1 over r to the 4th.
And that's the answer for one mode, or that's turning on all?
Yeah, that's for the one mode, and then per mode, and so up to, and the number of modes is L max squared. Okay, another possible objection. Now we'll start addressing.
Can I ask, for the high L modes?
Yep.
Oh, I see. Your source, even for the high L modes, is not localized near the horizon. It still extends out to.
Yeah, it's not. Yeah, it's not artificially tuned just to be L Planck outside the horizon.
And that's sufficient to counter a mining experiment that is localized near the horizon?
I think it's sufficient to do what you need to do there. Yeah, because we know that you introduce a string and you're sort of producing the modes, in the direction of the string, so to speak. But the flux you get is just an extra copy of the Hawking flux for each degree of freedom that can come out the string.
But what if the mining experiment isn't a string? What if it's lowering down a laboratory or something?
I would like to see a sharper version of that, and that's why I'm thinking about strings. Strings are a sharper version of that story. One could try to give a very sharp version of that within the context of a field theory description, but let's save that. Okay, so another possible objection which has been raised now is that generically this kind of scenario predicts extra flux. And that, so there's extra outgoing energy on top of what Hawking said. And that, it may look, well, it, again, you mean if J is purely classical? Yeah, but I told you J is secretly correlated with the internal states of the black hole. So ultimately, it may not look very coherent at all, but ultimately, it's got to contain all the information, which is exactly what we've been saying over the years. So, in the simple models, yeah. In these, yeah. So the answer is in these simple models, yes. Okay, and there's a question here. Okay, so let me develop this. So there's extra energy coming out of the black hole. Black holes decay more rapidly, at least in the simplest scenarios like this that I've described. And so that suggests a deviation from the expected thermodynamics. Namely, well, here's a quick argument. If you try to stick one of these things in a box and let it, or a black hole in a box and let it equilibrate, well, the energy is coming out more rapidly than Hawking said. That's the first equation over here. And so by detailed balance, if you wanted to equilibrate, you've got to have more energy coming in, and so you've got to be at a higher temperature. So the equilibration temperature is higher than the Hawking temperature, and then by the first law, that tells you that the number of black hole microstates is smaller than the Bekenstein-Hawking entropy, because of course this is what gives you the Hawking temperature. And so that at least seems to be a prediction of these simplest versions of the story. A very interesting question is whether you can find models that get the information out without extra energy flux. And in these models I described a while ago, models were found in sort of in the qubit or infinite temperature limit is what it really is. where you could have information transfer without extra flux. But in the more realistic finite temperature case, at least so far it appears that this is rather difficult to achieve. But that's a question for the future to really nail that down completely.
Steve?
Yep.
So I just thought of a problem here. So if it would seem like in this situation you really have different parts of the external system at two different temperatures. Because if I imagine I'm accelerating very close to the horizon, by your stipulation of nonviolence, I still see the Hawking temperature.
Well, if you're accelerating very close to the horizon, you see a much higher temperature than the Hawking temperature.
Wait, but I thought you said this is nonviolent stuff, so it's coming out
No, just an accelerated observer in the usual picture. If you're accelerated just outside the horizon, you see a very high temperature.
Oh, no, I meant the boost scaled temperature. So I mean,
yeah, it's the rescaled temperature.
But you see the same temperature that Hawking would have predicted.
Yeah. So
whereas the stuff coming out, if it's a higher temperature, it seems like parts of the system are at two different temperatures, and you could use that to run a perpetual motion machine.
Well, two answers to that. First of all, there are plenty of systems in nature which, for some purposes, have a temperature and some purposes don't. And an example is the sun. If you stick a thermometer near the sun, it registers about 6,000 degrees because that's the temperature of the photosphere. But if you were capable of measuring more finely what is coming out of the sun, you would discover that there are much higher energy neutrinos coming out.
Right, but the sun is not a thermal equilibrium.
It's not an equal. Yeah, so there's a question of what these things look like when they equilibrate, and I'm describing, first of all, the situation where you're just radiating into space and there's extra flux coming out. Ultimately, when they equilibrate, they've got to equilibrate at the same temperature. There are also solid-state systems where you have, sort of roughly speaking, nearly decoupled degrees of freedom that have different temperatures as well. And again, this only happens in an approximation.
Right, but just the whole firewall's problem is about equilibrated black holes in some sense, where we're talking about typical states.
Well, it's about evaporating black holes and what states contribute to typical black holes. You can also think about the equilibrium situation.
So if I can just translate, I think Steve is saying that his vision of it, he thinks that equilibrium black holes, whatever that may mean, may look very different from what we think of as astrophysical black holes. At least you're not committing to that.
I'm saying they have some different properties. Okay? There's extra flux that comes out, and that tells you equilibrate at a higher temperature.
But even with your extra flux, you are not yet modeling what you think of as an equilibrium black hole, or you are not yet claiming to model an equilibrated black hole.
Well,
you're modeling a post-page time black hole evaporating.
Yeah, well, that's what I started with, but I think the conclusion is that the model I've given tells you that in the end, if you do stick it in a box and try to equilibrate it, there are modifications.
Right, and Aaron is claiming that
there
must be further modifications. It really shouldn't look like a black hole if it's going to satisfy the second law of thermodynamics.
Well, okay, so this is something to pursue, I think, offline. And that's a good question about whether you really get into a serious quandary there or not.
Can I ask another question?
Yeah. Mm-hmm.
So I might have thought that you have this extra process which is radiating stuff outward. I might have thought that if, for example, I knew the theory and the state of the black hole in advance, I could, at this moment, cook up some carefully contrived signal that would go in and be absorbed into the singularity through your extra non-local interaction in just such a way as to cancel your extra outgoing stuff. I could try to equilibrate just that process, so to speak, and let the Hawking process continue to run, in which case I get an overfull black hole.
Well, one should think that through. I think, one needs to be, to think through that kind of thing. One comment, this is the kind of thing I'm describing is a big relative correction to the amount of stuff that gets out. Because classically, stuff doesn't get out of a black hole. It's a small correction to the stuff that gets in, because classically, everything that you send into a black hole at higher frequency than the inverse Schwarzschild radius, within the right area, everything goes in. So it's a relatively small correction to that. So one would, I think, have to think through carefully how much of an impact that relatively small correction has.
But that has not yet been thought through about whether those kind of...
Not all things have been thought through, here or in other scenarios. Okay. All right. So the page curve, this is the page curve, would go up the entropy of the radiation and then down the Bekenstein-Hawking curve, basically following, along these, the minimum of these two upper curves. In this story, apparently would be modified. You have fewer internal degrees of freedom of the black hole than predicted by Bekenstein and Hawking, and you come down sooner. And an important question is, does this present a contradiction with anything we really know? If it does, then that's a constraint going backwards on these kinds of models for how information gets out. But if it doesn't, then we're in good shape. And so we could discuss further thoughts on that. But since time is short, let me at least finish finish with some comments on all of this. With a few comments, and talk a little bit about the bigger picture, which I think relates to Tom's talk. So first, the horizon is, in a sense, special. We do violate the equivalence principle in such a picture. Really, I think the proper way of thinking about that is that there's, in the more fundamental framework, a generalization of the equivalence principle. But it's a small effect for a big black hole. It's not sharp. It's sort of spread out over scales of size of the black hole. A second comment regards this question of non-locality and acausality, which conventionally are linked by the symmetries of Minkowski space. But here, if you have information transferring into a black hole and transferring out at some later time, you can perfectly well have that happen and preserve the asymptotic causal ordering because of the symmetries of the black hole background are just different than those of Minkowski space. And so it seems that this kind of non-locality does not necessarily place causality at risk. And we might go one step further and, of course, you want to think about people falling into the black hole, but you might conjecture that, that there's a sensible scenario here with these fairly mild interactions that tell you there's no observable violation of causality. That's something that, again, we need the fundamental description of all this to really.
So are you thinking there'll be an effective causal ordering of the points of the classical black hole that is different that makes some space-like points causally related to each other that you could actually write down?
Yeah, well, for example, you could a way of trying to convince yourself there's a problem is, well, if you do make extreme boosts on people inside the black hole. So, for example, you could think about the nice slices at very long times and so on and so forth. But we have good reason to expect that there are problems with such things, first of all. And second of all, the interactions I've described are sort of creating quanta over the whole size of the black hole. They're not really creating quanta at very short distance scales inside the black hole. Okay.
You want to complete and then should ask you this? I just wanted to ask you something on this particular.
Well, I should finish in 5 minutes, right?
We've been elastic, but are you close to that?
Pretty close. Depends on how many questions, but pretty close.
But okay, so my question was, if you had a Hamiltonian of the kind you had previously,
yes. Yeah.
I don't see how you will avoid getting a non-zero commutator of a local operator outside, a field operator outside, and a field operator inside.
Right, yeah.
And I think that
question
commutator...
is, how big is that and how bad is
Well,
that?
it'll be 1 by r cubed, as you estimated.
No, that is the size of the effective source outside. That's not the size of the interaction.
Well,
but anyway, yes,
I mean,
we do have to do things that are non-local with respect to the local quantum field theory semi-classical.
I just want to say, at the same order of non-locality, I don't see how you will avoid acausality. I mean, these points are space-like separated.
Well, they are space-like separated, but the question is, how could you turn that into a scenario where you could kill your grandmother? And it's not so easy. So, I mean, that's the usual problem in flat space, right? You can turn this kind of signaling by using the symmetries into a scenario where you could kill your grandmother. Okay, let me quickly make a comment about complementarity, starting with an apology to Lenny. So a while back, I wrote a paper where I basically said I don't understand complementarity for various reasons. Now, of course, complementarity has been assaulted by AMPS, so I don't feel like I really need to apologize that much. They shouldn't. But I sent him this email, and I never got a response, so I don't know what happened. So anyway, this was the email.
Maybe it was just waiting till now.
Yeah. But I'm going to revise this because I have at least a thought for how you might understand complementarity, which I think is not quite what was said, but maybe helps. So it seems that there may be a way to make sense of a certain form of complementarity. So first of all, well, how should we think about it? One perspective connected to the classical story is complementarity results from not a Bohr-like complementarity, but from different ways of describing things from the point of view of different gauges. So here I've put in a slicing, so at least that would classically specify sort of a gauge, a choice of coordinates. And in the way I've been describing things, information comes in, and then information comes out. And of course, by the time a bit gets out, basically, if you had tried to track it, say, on a nice slice all the way back, that bit would have had to have been erased. You can't have it in two places at the same time, and time is, along that slice. So there's sort of a weak complementarity that's necessary and is related to, why nice slices are bad, et cetera. But you could just as well choose a different gauge or choice of description of your space-time where you have slices that stop at the horizon. And in that point of view, you do have, if you sort of follow the logic of this picture, a picture where information comes in to near the horizon and in some sense ultimately has to be erased and transferred out into the outgoing radiation. So this is not really Bohr-like. It's an equivalent, a gauge equivalent descriptions, I think, in some sense. But in this picture, there's, in this gauge, there's no interior. That's related to the classical picture, I think. In the classical picture, in this gauge, there's no interior.
So, Steve?
Yes.
If this is the picture for information to fall in and come out,
yeah.
Wouldn't an infalling observer notice something?
Well, okay, so you've got to represent the dynamics of an infalling observer in this gauge. So there's a question of how you, and that, by the time you perform the transformation to describe the infalling observer, you're basically switching over to something like the other gauge. That's the idea. Okay, let me close by saying I've only given an approximate, incomplete description of how I'm suggesting things work, which is, I propose to avoid or evade certain problems, but there is the question, what's the fundamental theory? And I've touched on that in suggesting this picture involving quantum subsystems. Let me just say a few more words about this, and it sort of relates to some of the things Tom says. So you might ask, if we don't have space-time as the fundamental structure, what is? And one possibility is certain Hilbert spaces with networked factor structures in addition. So I have in mind something like this picture where you have factors of a Hilbert space, and those factors should be thought of as describing a localization which roughly corresponds to space-time localization. And we should compare how local quantum field theory works. Again, local quantum field theory not being the exact picture. We know that space-like separated operators create states, well, they commute, and so they create sort of independently different factors of the Fock space. And so this is an attempt to think about a way of generalizing that kind of construct and think about locality in this more general context. So you might guess that you could build up some quantum analog of a manifold with an appropriately chosen tensor network structure. It's not quite the same as, I don't think, as the tensor networks that Juan was describing, and other people have thought about it. It's a different kind of construction with some common ideas with the algebraic description of quantum field theory, which is also based on causal diamonds. And Tom is describing at least one version of this kind of story. I think he has a lot of extra structure that I wouldn't necessarily put into it, but at least this notion of overlapping and linked factors is, I think, part of what we're both saying. And then on that, you have unitary evolution, and ultimately it should well approximate local quantum field theory in appropriate situations. And then you might ask, where does locality come from? And the unitary evolution has to have certain conditions built into it. So this is just a sketch of how, an idea for how things would work. The evolution has, a certain kind of locality respecting this subsystem locality. And then you can think about where symmetries come from. So a global symmetry is a transform of the whole Hilbert space. Local symmetries transform the independent factors differently, et cetera. So at least this is one way of approaching the question, which would need to be fleshed out a lot. And Tom has some ideas about, again, how to flesh out something at least similar. This is how to approach the question of giving a more fundamental framework. So in summary, I've asked the question, can we describe the information transfer necessary to save quantum mechanics without violent departure from semi-classical physics? And I've given what I think is evidence, and I hope I've convinced some, that you can, and that firewalls are banished. They should be banished. There's a deeper question. What does this tell us about the more fundamental framework? And we're just getting started in that direction, but at least I think these ideas of network factors are worth pursuing. So I'll stop there. Actually, I won't quite stop there. Well, I made a little table of a scorecard, but anyway. Okay. Yeah.
So this is related to the picture, the physical picture you gave of an antenna sending out signals. Of course, your work spans a lot of technical work, and I don't know if you want to revisit that picture, but I just have a question related to the picture you gave. If an antenna is emitting some signals, and I send in a wave on it, it won't have a universal response while going into the antenna because it's emitting. So how is it? This won't be non-violent in that sense, right? You're saying that the outgoing thing carries information. I reflect it by a mirror, or I throw in some other signal, and it's supposed to have a universal response with the antenna. That doesn't work with normal antenna.
Well, sorry. Let's back up. So I'm parameterizing small corrections to the ordinary dynamics of a black hole. Mm-hmm. And the ordinary dynamics of a black hole is I have a black hole, I send in a photon with a smaller wavelength, and it just goes in. Information transfers from outside to inside, the information theory way of thinking about it.
So you're talking
That's the order zero dynamics, so to speak, right? And so there are small corrections that transfer information out. And then you're asking, I think, a question related to if I send a photon in, what happens to it?
Of the same scale as the one which typical scale.
So what happens is the dominant process is still the process that was the only process is still the dominant process. And the process that was the only process was the photon just goes in. And there's a small correction to it.
But while going out, it's a big correction, and while going in, it's a small correction, or both are small?
It's relatively small, right? Okay, so the standard semi-classical description of a black hole, stuff goes in, right? And at least stuff carrying information does not come out. Okay, so that's the zeroth order process. And then we have some corrections that are small as compared to the zeroth order process. So for example, may relay only 1 bit per light crossing time. And that bit may have an energy of order, the inverse size of the black hole. So it's a small effect relative to the sort of the zeroth order Hamiltonian I just described. But it's not small relative to the Hawking radiation.
But it's tied to the black hole not having, any of the e raised to power s states. So the information content.
Not having.
The information content of the black hole is smaller than the Bekenstein-Hawking entropy.
Well,
I can't reconcile this with a full black hole, like having as much information as the S. Bekenstein.
Well, sorry. So let's back. I think there are two different issues you're touching on here. But yeah, what I said is at least in these simpler scenarios, and possibly generically, but at least in these simpler scenarios, you do end up, apparently, unless there's some loophole in what I said, with the conclusion that the black hole entropy, so the number of states, is smaller than given by Bekenstein and Hawking.
Do you see any way to connect this to things we thought we previously understood about quantum gravity, like string theory or matrix theory?
Well, I thought I heard you yesterday. Well, Joe and I have had many debates over time about whether ADS-CFT, for example, which is supposed to be the best non-perturbative definition of string theory, or was, exactly describes what goes on with black holes. We've had many, many debates which have at some times gotten rather heated. And I thought I heard Joe yesterday say that we need a completely new theory of the bulk.
Well, I didn't say completely new because in fact, you're modifying gravity outside the horizon at a level which would also modify Witten diagrams, presumably. I mean, you're modifying quantum field theory at order. If you modify the flux at order 1, you're modifying Witten diagrams at order 1. And so now we don't know that Witten diagrams are right, but if we assume that much of the duality, then I think this idea can be sort of tested within ADS-CFT, and certainly is inconsistent, I think, with our usual understanding of how to calculate an ADS-CFT.
Well, okay. So again, I think that I've expressed some questions about whether and how ADS-CFT gets the ultimate right story with regard to black holes. And at least I think I've seen some reflection of those questions recently, but they're still quite valid. How does it do it? And I think we don't know. So let's see if it does, and if so, how.
Is this scenario similar to saying that the modes, the regular modes outside the horizon are? So is this scenario similar to saying that the Ringler modes outside the horizon are not in a thermal density matrix, but they are in a particular pure state, which is similar to the density matrix, and that contains the information about the black hole? Is that more or less similar?
Not quite, because at least the way I've described it, and there's some latitude here. Well, so you have at least in the simplest version, where this with this extra source. So you have the ordinary Hawking radiation, which is looks very excited from the Rindler point of view. We know, although that's a mirage. And then, in addition, you have these sources which are exciting outgoing excitations. Those are not purely, at least ultimately, those are not just Rindler modes.
Well,
okay.
I was just
and
wondering
moreover,
whether
they're created not just at the horizon, but in this whole region of order the size of the black hole in size.
So I had a comment, and I had a couple of comments, actually. So one of them is at the first
and I
column.
can explain what I mean by it.
No, I understand, but I just went. I just wanted to emphasize that a lot of these A equal to RB scenarios are designed to have precisely the kind of non-violent non-locality you're speaking about. So you can argue about whether they're right, but the attempt is at least to get a semi-classical space-time out.
Okay.
Maybe you don't agree it comes out.
Let me explain one small piece of this, and that is, I think Lenny said he and all sensible people believe in some version of A equals RB or some word. Am I mangling what you said?
I believe that I said in my talk that A equals RB is wrong.
No, you said some version of that is right, or at least all sensible people. I forget. We could look up the recording. Did someone else hear this, or am I losing my mind? Okay, I saw one had. No, again, but some version of it. That's the qualification. Generalized. That's what I mean by general.
I don't think it's at all a contradiction to say all sensible people believe something wrong. It seems an obvious deduction from this.
Okay, so, but on that note, but this is, that kind of scenario, I think the kind of scenario, at least the octopus, is something that is really non-localized, if I've heard properly, on enormous scales as compared to the black hole. It's a departure from the usual local description on enormous scales. And so, yes, maybe that is somehow nonviolent if you can ultimately make sense of it and recover some approximation of semi-classical space-time over here in some complementary sense. I don't know how that works, which is why I put next there. I don't know who does. You guys are trying to describe such a scenario. And one of the points I want to make here is this is sort of the right size for non-locality or departure from locality. This is sort of too hot, and this is too cold. This is just right. In the firewall story, you have non-locality just right to the horizon, but not a Planck length further.
Okay. Just one more answer to Joe's question also, I think. If you could make these non-local effects smaller so that they're exponentially small, and I think you could probably get information out we can discuss, but then you wouldn't need to answer this question about what effect do you know about, right? Then is that, would you agree with that? You're worried about this because they're power law.
Again, it's couplings versus rates, and I claim that, okay, we can discuss what couplings are necessary to give the rates, and that involves the number of internal states, so in some sense can be naturally small. But the rate is of order 1 as compared to the Hawking rate. And we know that because the departure from or the page curve or some new version of it has to fall, has to depart by a certain size from the naive Hawking curve, which just goes up to the Bekenstein-Hawking entropy when the black hole evaporates. So in that sense, we need an order 1 effect.
So my question is about the entropy of the black hole.
The entropy?
Entropy?
Yeah.
So in string theory, we think we have a good understanding of the entropy of black holes from calculations of counting of black hole microstates in various scenarios.
In certain cases, and that's part of the caveat here.
So you had a scenario where the entropy of the black hole was less than the Bekenstein-Hawking entropy. So I was wondering, can you quantify how much less, and is this contradicting what we expect from string theory?
Well, in string theory, I don't think this goes back to the question I asked. Is there something we really know that contradicts that picture? And, so we don't have a count of the microstates of a Schwarzschild black hole, of a black hole in this region. In the, in strongly coupled gravity, we just don't have one in string theory. ADS-CFT provides certain hints that the value is the Bekenstein-Hawking entropy if ADS-CFT is an exact correspondence. Anyway, and finally there are counts, say Strominger-Vafa in the extremal or near extremal regime, and also in the weakly coupled regime. And so, do those provide contradictions? I don't know, and I think it's worth thinking about. This is another case where what we should think about, and that's where we have sort of our best version of getting a count of the microstates from the boundary theory. And what is the full description of formation and evaporation of 2 + 1 dimensional black holes, and how does that match up with the boundary theory? And that's one place to think about what happens and whether how that would match up with this story. Yeah. Yeah, and you get of order the Bekenstein-Hawking entropy. Well, at least the simplest let me give you just a naive estimate. Don't take this too seriously. I should probably state that twice for the record, since people like to quote things with that caveat as if that caveat had not been added. But let's just be really simple-minded, and let's say that you need twice the flux of the extra radiation as compared to the Hawking radiation. So that means the Bekenstein-Hawking entropy would be large by an order 1 factor from the true black hole entropy.